Welcome. Take a deep breath, settle into comfort, and prepare to journey into one of nature's most beautiful paradoxes. Tonight, we explore glass, a material so familiar that we barely notice it, yet so strange that after thousands of years of human use, it still puzzles the greatest minds in physics. Let us begin with a simple question. What is glass, really? If you were to ask a physicist this question, you might expect a straightforward answer. After all, we can describe water, we can describe ice, we can describe steel. But glass? Glass resists easy categorization. Glass exists in a twilight state between the orderly world of solids and the fluid chaos of liquids. Scientists use a particular term for this. Glass is an amorphous solid. Amorphous, from the Greek, meaning without form, without shape, without the crystalline structure we expect from solid matter. Think about the window near you, if there is one, or perhaps a drinking glass, a mirror, the screen of a phone. These objects feel solid. They hold their shape. You can tap them, and they ring with that distinctive glassy note. They are, by every measure of our everyday experience, undeniably solid. And yet, if you could shrink yourself down to the atomic level, if you could observe the arrangement of atoms within that glass, you would find something deeply unexpected. You would find disorder. The atoms in glass are frozen in a disordered, liquid-like arrangement. Imagine a snapshot of water, caught mid-flow, suddenly stopped in time. The molecules have not had the opportunity to arrange themselves into the neat, repeating patterns that characterize crystals. In a crystal, salt, diamond, quartz, every atom knows its place. The structure repeats predictably, infinitely, like a three-dimensional wallpaper pattern extending in all directions. But in glass, there is no such order. The atoms are jumbled, chaotic, irregular. They sit where they happen to be when the material became too viscous, too thick, too sluggish to allow them to rearrange into proper crystalline order. This creates an extraordinary situation. Glass mechanically behaves like a solid under everyday conditions. Drop it, and it shatters. Press on it, and it does not yield. It maintains its shape against gravity, against pressure, against time itself. For all practical purposes, glass is solid. And yet, examine its internal structure with X-ray crystallography or neutron scattering, and the evidence tells a different story. The atomic arrangement resembles that of a liquid, random, disordered, without the long-range periodicity that defines crystalline solids. So we arrive at this peculiar duality. Glass has a liquid-like atomic structure, yet solid-like rigidity. It is a contradiction, a material that refuses to fit neatly into our conventional categories of matter. We teach children about the states of matter, solid, liquid, gas, and these categories work remarkably well for most substances. Water freezes into ice, a true crystalline solid. Heat it, and it melts into liquid water. Heat it further, and it evaporates into gaseous steam. Clean transitions, clear boundaries, but glass does not play by these rules. This is why researchers describe glass as a liquid-solid hybrid. It occupies a strange middle ground, exhibiting properties of both states simultaneously. The phrase might sound like a compromise, a verbal shrug from scientists who cannot quite pin down what glass truly is. But it is more than that. It is an acknowledgement that glass represents something fundamental about the nature of matter itself, something we do not yet fully understand. And here is where our story deepens into mystery. Despite centuries of glassmaking, despite our technological dependence on glass in everything from architecture to fiber optics, despite intensive research by brilliant physicists and chemists, there is no universally accepted theory of the glass transition. Think about that for a moment. We can predict the behavior of black holes at the edge of the universe. We can describe the quantum mechanical behavior of subatomic particles with extraordinary precision. We can model the protein folding in living cells. But we cannot fully explain how glass becomes glass. The glass transition, that moment when a liquid becomes glass, remains elusive to complete theoretical understanding. Competing models attempt to explain how molecules lock up during this process. Some theories focus on the way molecules become caged by their neighbors, trapped in local configurations that prevent long-range rearrangement. Other models emphasize cooperative motion, the idea that molecules must move together in increasingly large groups as the temperature drops, until finally the coordination required becomes so extensive that movement essentially ceases. Still, other approaches invoke concepts from thermodynamics, kinetics, or even ideas borrowed from the study of complex systems and emergent phenomena. Each of these models captures something true about glass. Each makes predictions that match certain experimental observations. But none has achieved the status of a complete, comprehensive theory that satisfies all researchers and explains all aspects of the glass transition. The scientific community remains divided, not contentiously, but productively, with different schools of thought pushing understanding forward from different angles. Part of the challenge lies in the nature of the glass transition itself. The glass transition is not a sharp phase change like melting. When ice melts, there is a specific temperature, 0 degrees Celsius at standard pressure, where solid becomes liquid. You can measure it precisely. The transition happens at a definite point. Energy goes into breaking the bonds of the crystal lattice, and the temperature remains constant during the phase change. It is clean. It is clear. It is a true thermodynamic phase transition. But the glass transition is not like that at all. As a liquid cools toward becoming a glass, there is no single temperature where the transformation occurs. Instead, there is a range, a region where the material gradually, continuously changes its character. The liquid becomes thicker, more resistant to flow. Its viscosity, that measure of a fluid's resistance to flowing, begins to climb. And it does not just increase a little. The viscosity increases by many orders of magnitude as glass forms. Let us pause to appreciate what many orders of magnitude means. An order of magnitude is a factor of 10. Many orders of magnitude might mean 1,000,000 times more viscous, or 1,000,000,000 times, or even more. Imagine honey versus water. Honey might be 1,000 times more viscous than water. Now imagine something 1,000,000 or 1,000,000,000 times more viscous than honey. The liquid slows and slows and slows until it effectively stops flowing on any timescale that matters to human observation. It has not frozen in the sense that water freezes into ice. There is no crystallization, no sudden structural transformation. The molecules have simply become so sluggish, so reluctant to move, that the material behaves as a solid even though its structure remains disordered. This gradual nature of the glass transition makes it extraordinarily difficult to study, and even harder to theorize about. Where exactly does liquid end and glass begin? Different measurement techniques give different answers. The transition temperature depends on how fast you cool the material. Cool it quickly, and you get glass at a higher temperature. Cool it slowly, and the molecules have more time to explore possible arrangements, and the transition happens at a lower temperature. This rate dependence is not a feature of true phase transitions. It is a signature of something more subtle, more complex. And so, after all our exploration, after all our technological achievements with glass, after all the research and experimentation and theoretical work, we must admit a humbling truth. Glass remains one of physics' unsolved problems. Not unsolved in the sense that we know nothing about it. We know a great deal. But unsolved in the sense that we lack a complete, fundamental understanding of why glass behaves the way it does. We cannot yet write down the equations that fully describe the glass transition from first principles. We cannot yet predict, with certainty, which materials will form glasses easily, and which will stubbornly crystallize instead. This should not discourage us. Rather, it should fill us with wonder. Here is a material that humans have been making for at least 5,000 years. A material that we have shaped into vessels and windows, into lenses and telescopes, into fiber-optic cables that carry information across continents and beneath oceans. A material that has changed human civilization, that has expanded our vision literally and metaphorically. And yet, at its most fundamental level, glass keeps its secrets. In the quiet moments before sleep, there is something deeply satisfying about contemplating such mysteries. The universe is not fully known. There are still questions without complete answers. Glass, ordinary glass, reminds us that wonder exists not just in distant galaxies or exotic subatomic particles, but in the everyday objects around us. The window, the mirror, the screen. Each is a small monument to a phenomenon that nature has not yet fully explained to us. So as you rest, think of glass. Think of its frozen disorder, its solid liquidity, its quiet refusal to fit our categories. Think of the researchers still working to understand it, building models, running simulations, conducting experiments. And take comfort in knowing that the world still holds mysteries, even in the most transparent, most ordinary, most familiar of materials. Glass is waiting to be fully understood, waiting with the patience that only a nearly frozen liquid can possess. Waiting in windows and on tables, in laboratories and in homes, maintaining its beautiful contradiction. A liquid that thinks it is a solid that remembers it was a liquid, a material suspended between two worlds, belonging fully to neither. And that is where we will leave the fundamental mystery for now, suspended like glass itself, neither resolved nor abandoned, but simply present, real, and endlessly fascinating. Rest now, and let these thoughts settle like molecules in cooling glass, finding their place in the quiet structure of sleep. There are stories we tell about glass that have taken on lives of their own. Stories that sound plausible, that seem to explain what we see, and yet turn out to be beautiful fictions. One of the most persistent of these is a tale you may have heard yourself, perhaps in a museum, perhaps in a classroom, perhaps from someone gesturing at the windows of an old cathedral. The idea that window glass flows over centuries is a myth. It is an appealing myth, to be sure. Stand before the stained glass windows of a medieval cathedral, and you might notice that some panes are thicker at the bottom than at the top. The glass appears to have slumped, to have gradually yielded to gravity over hundreds of years, flowing downward like an extraordinarily slow river. This observation has been used for generations as proof that glass is really a liquid, just an incredibly viscous one, still flowing even in window panes, still in motion, just barely perceptible over the span of centuries. But this explanation, as charming as it is not correct. The uneven thickness in old panes comes from manufacturing methods, not from flow. Before modern float glass processes revolutionized glass production, window glass was made by very different techniques. Glassblowers would create large discs by spinning molten glass, or they would blow cylinders that were then cut and flattened. These methods simply did not produce uniform thickness. A pane might be thicker on one edge than another not because of any inherent property of the glass itself, but because of the limitations of the manufacturing process and the skill of the craftsperson. When glaziers installed these uneven panes, they often quite sensibly put the thicker edge at the bottom. This provided better stability, better support. It was a practical choice, not evidence of flowing glass. The pattern we observe in old windows, thickness at the bottom, reflects human decision-making during installation, not the patient flow of glass over time. And when we actually calculate how long it would take for glass to flow at room temperature, we discover something remarkable. Any real flow at room temperature would take longer than the age of the universe. The mathematics are unambiguous. At the temperatures that window glass experiences, even in the warmest climates, even over centuries, the viscosity is so enormously high that meaningful flow simply does not occur on any timescale relevant to human civilization, or indeed to geological time. The glass in a medieval window is not flowing. It will not flow. Not in 1,000 years, not in 1,000,000, not in 1,000,000,000. Yet here is where the story becomes more subtle, more interesting than a simple myth-busting exercise. Glass can, in principle, flow extremely slowly. The difference between can in principle and does in practice is vast, but it is important. Glass is not absolutely rigid at the atomic level. At any temperature above absolute zero, atoms vibrate, jiggle, occasionally hop from one position to another. In glass, these movements are extraordinarily rare and extraordinarily small at room temperature, but they are not strictly impossible. Given enough time time measured not in centuries, but in periods that dwarf the current age of the universe, glass would indeed flow. But this is a theoretical possibility, not a practical reality. The myth of flowing window glass contains a kernel of theoretical truth, wrapped in layers of misunderstanding about timescales. What makes glass even more fascinating is what happens as it forms, as it transitions from liquid to that frozen, amorphous state. As glass cools toward the glass transition, it does not behave uniformly. Glass exhibits dynamic heterogeneity as it cools. This is a remarkable phenomenon, one that scientists have only been able to study in detail in recent decades, using sophisticated experimental techniques and computer simulations. Dynamic heterogeneity means that not all parts of the cooling liquid behave the same way at the same time. Some regions move while others are nearly frozen. Imagine a crowd of people slowly coming to a stop. Some individuals stop moving almost immediately. Others continue to shuffle, to adjust their position, to move around. Eventually everyone stops, but not all at once, and not in a uniform way. The glass-forming liquid is similar. At the molecular level, there are regions where molecules remain relatively mobile, able to rearrange and explore different configurations. Right next to these mobile regions, there are other areas where molecules have already become sluggish, nearly locked into place. These heterogeneities are not static. They appear and disappear, shift and change. A region that was mobile might become frozen, while a neighboring region that was frozen might suddenly become mobile again. The patterns are transient, flickering through the material like shadows. But as the temperature continues to drop, the frozen regions become more prevalent, more persistent, more extensive, until finally the entire material has become a glass, with only the tiniest, slowest molecular motions still possible. This dynamic heterogeneity is one of the keys to understanding why the glass transition is so complex. The material does not transform uniformly. Different parts of the liquid approach the glassy state at different rates, in different ways. This makes the transition smooth and gradual rather than sharp and sudden. It also makes it extraordinarily challenging to develop a complete theory, because any successful theory must account for these spatial variations, these temporal fluctuations, this fundamental non-uniformity of the process. And even after glass has formed, even after it seems to have settled into its final state, the story is not quite over. Some glasses show aging for decades after formation. This is not aging in the sense of deterioration or decay. It is a more subtle process. The glass, which seemed to have reached a stable configuration, continues to very slowly relax. The atoms continue to make tiny adjustments, gradually settling into slightly lower energy arrangements. The material is still exploring its energy landscape, still searching for more stable configurations, but doing so at such a glacial pace that the changes are barely detectable except through careful measurement over long periods. These aging effects are real and measurable. Properties like hardness can slowly change over time. A piece of glass might become slightly harder, or its density might increase very marginally, or its refractive index might shift by a tiny amount. These changes are small, but they are significant for certain applications. For precision optical instruments, for instance, even tiny changes in properties over years or decades can matter. Scientists and engineers who work with glass must account for this aging, this slow evolution, this reminder that glass has not truly reached equilibrium, but is merely moving toward it at an imperceptibly slow rate. The phenomenon of aging reveals something profound about glass. It is not a static material frozen in time. It is a material frozen in the process of becoming something else, never quite able to complete the journey. It is trapped in a state of perpetual, almost imperceptible transformation. Now let us expand our understanding of what glass can be. When most people think of glass, they think of the transparent material made primarily from silica, sand essentially melted and cooled. But the glass state is not unique to silica-based materials. Many substances can form glasses if cooled rapidly enough to prevent crystallization. And among the most remarkable of these are metallic glasses. Metallic glasses share the same amorphous disorder as conventional glass. Take a metallic alloy, a mixture of metals like iron, nickel, boron, and others in carefully chosen proportions, and cool it extraordinarily quickly. Cool it so fast that the metal atoms do not have time to arrange themselves into the orderly crystal structure that characterizes normal metals. What you get is a metallic glass, a material that is metallic, that conducts electricity like a metal, that looks like a metal, but that has the disordered atomic structure of glass. These materials are extraordinary. They combine properties in ways that seem almost impossible. These metallic glasses can be stronger and more elastic than steel. Think about what that means. Steel is already one of our strongest, most useful structural materials. We build skyscrapers with it, bridges, ships. And yet metallic glasses can exceed steel's strength, while also being more elastic, able to deform and return to their original shape to a greater degree than steel can. This combination of strength and elasticity comes from the disordered atomic structure. In a crystalline metal, there are regular planes of atoms that can slip past each other under stress, leading to permanent deformation. Metallic glasses lack these regular planes. Their disorder makes it harder for such organized slipping to occur, which increases strength. At the same time, the disordered structure can accommodate more elastic deformation because there is no rigid crystal lattice that must be maintained. Metallic glasses also resist corrosion better than many crystalline metals because they lack the grain boundaries where corrosion often begins. They can be excellent magnetic materials. They have found applications in high-performance sports equipment, in transformer cores, in precision instruments, in situations where conventional metals do not quite have the right combination of properties. The discovery and development of metallic glasses has expanded our understanding of what glass itself means. Glass is not just the transparent substance in windows. Glass is a state of matter, a way of organizing atoms, a category that includes many different materials unified by their amorphous structure and their mode of formation. Silicate glasses, metallic glasses, polymer glasses, organic glasses, all share this fundamental characteristic of disorder, of being frozen liquids, of occupying that strange intermediate territory between crystalline solid and flowing liquid. The existence of metallic glasses also reinforces how strange and special the glass state really is. That you can take something as different from window glass as an iron-based alloy and produce essentially the same type of amorphous structure, the same type of transition, the same type of behavior, suggests that glass represents something fundamental. It is not a quirk of silica. It is a general phenomenon, something that emerges from the basic physics of how matter behaves when cooled rapidly enough to prevent crystallization. As you rest now, consider the strangeness of glass anew. Consider that the medieval windows have not flowed, though the myth persists. Consider that glass continues to age, to evolve, to slowly change for decades after it seems solid and stable. Consider that regions within cooling glass move at different rates, creating a flickering landscape of mobility and stillness. Consider that metals themselves can be transformed into glass, becoming stronger than steel while maintaining the same fundamental disorder that characterizes the glass in a window. Glass confuses scientists not because they lack tools or intelligence, but because glass itself is genuinely complex. It exhibits behaviors that seem contradictory, transitions that seem gradual yet definite, structures that seem liquid yet solid, aging that seems like motion yet proceeds immeasurably slowly. It defies simple categorization because it exists at the boundaries of our categories, in the liminal spaces between the states of matter we learned about as children. And this is not a failure of science. It is an invitation. Glass invites deeper investigation, more subtle theories, more creative experiments. It reminds us that nature is under no obligation to fit neatly into our conceptual boxes. Sometimes nature creates things that are genuinely in between, genuinely paradoxical, genuinely mysterious, even after sustained study. So let the myths fall away, but let the wonder remain. Glass does not flow in our windows, but it can flow in principle, given unimaginable spans of time. Glass appears solid and stable, but it ages and changes, imperceptibly slowly. Glass seems uniform, but it forms through a dance of heterogeneous motion. Glass seems unique, but the glassy state appears in materials as different as sand and steel. These are not contradictions that need resolving before we can sleep. They are simply the nature of glass, complex and fascinating, familiar yet strange, understood yet mysterious. Rest now in the presence of these paradoxes, these gentle confusions, these reminders that the world is more intricate than it first appears. Long before humans learned to create glass in workshops and furnaces, nature was already making it. Deep within the earth, in chambers of molten rock, in the violent eruptions that shaped landscapes and terrified early peoples, glass was being born. Natural volcanic glass, such as obsidian, was humanity's first glass. Obsidian forms when lava cools so rapidly that crystals have no time to grow. The molten rock, rich in silica, erupts from a volcano and meets air or water. The temperature drops suddenly, dramatically. The atoms, which would ordinarily arrange themselves into the orderly structure of crystals like quartz or feldspar, find themselves frozen in disorder. The result is obsidian, volcanic glass, usually black or dark in color, smooth and lustrous, with a texture unlike any other stone. To early humans, obsidian must have seemed magical. Most stones are grainy, rough, with visible crystals or a dull surface. But obsidian is different. It catches light. It reflects. When broken, it does not fracture along crystal planes, but creates what geologists call a conchoidal fracture, a smooth, curved break that produces edges of extraordinary sharpness. Sharper, in fact, than even modern surgical steel. At the molecular level, an obsidian edge can be only a few molecules thick, creating a blade of almost unimaginable keenness. And so, obsidian was used for razor-sharp tools and ritual objects. Archaeological evidence shows that obsidian tools appear remarkably early in human prehistory, wherever volcanic activity had deposited this natural glass. Obsidian blades could cut hide, slice meat, carve wood with an efficiency that stone tools made from other materials simply could not match. A knife made of obsidian was a prized possession, a tool of superior quality that made the work of survival easier. But obsidian was more than merely practical. Its beauty, its luster, its deep color, and the way it seemed to hold darkness within it, gave obsidian a ritual significance. It was used to make ceremonial blades, religious objects, mirrors polished to a reflective sheen. In Mesoamerica, obsidian mirrors were associated with shamanic practice, with divination, with seeing into other realms. The Aztecs believed that the god Tezcatlipoca, whose name means smoking mirror, could be perceived through obsidian. The material that nature had made by accident became woven into mythology, into ritual, into the sacred dimensions of human life. Obsidian also became one of the first materials to be traded over long distances. Because volcanic glass only forms where there are volcanoes, obsidian sources were geographically limited. A piece of obsidian found in an archaeological site hundreds of miles from the nearest volcano tells a story of trade routes, of exchange networks, of human connections that spanned landscapes. Archaeologists can trace obsidian artifacts back to specific volcanic sources through chemical analysis, mapping ancient trade routes through the distribution of this natural glass. For thousands of years, obsidian was the only glass humans knew. It was a gift from the earth, from fire and sudden cooling, from geological processes beyond human control or understanding. But humans are curious, inventive, persistent. And eventually, someone discovered that glass need not be merely found. It could be made. The earliest man-made glass appeared in Mesopotamia and Egypt. This occurred around the mid-3rd millennium BCE, roughly 5,000 years ago. We do not know the exact date, the exact moment, because these discoveries happened before writing had developed sufficiently to record them, or the records that existed have been lost to time. What we have are the artifacts themselves, beads of glass, small and precious, colored with minerals and oxides, strung onto necklaces or sewn onto garments. These earliest glass objects were not vessels, not windows, not large functional pieces. They were small, decorative, valuable. Glass in these early days was not a common material, but something rare and precious, worthy of burial with the dead, worthy of inclusion in royal treasures. The technology to make it was limited, specialized, perhaps secret. How did humans first discover that they could make glass? The honest answer is that we do not know for certain, but there are compelling theories. Early glass likely began as an accidental metalworking byproduct. Imagine a Bronze Age furnace, burning hot to smelt copper or tin, or to alloy them together into bronze. The furnace might be built of stones, perhaps stones containing silica, perhaps lined with sand to protect the structure. Wood or charcoal burns, temperatures soar, and minerals begin to melt and combine in unexpected ways. Silica, the primary component of glass, melts at a very high temperature, around 1,700 degrees Celsius. Too high for most ancient furnaces. But if certain other substances are present, sodium compounds, for instance, which might come from plant ash used as fuel, or from the natron deposits common in Egypt, the melting point drops dramatically. Ancient metalworkers, tending their furnaces, might have noticed strange, glossy puddles forming, substances that were not metal, but also not stone, something new and strange. At first, these glassy formations might have been curiosities, byproducts to be discarded. But someone noticed their beauty. Someone experimented. Someone discovered that by deliberately combining certain materials and heating them in the right way, this glassy substance could be produced reliably. The art of glassmaking was born, not from a single flash of inspiration, but from observation, experimentation, and the gradual accumulation of practical knowledge. The ancient recipes, as we understand them from later texts and from analyzing ancient glass artifacts, used silica-rich sand as the primary ingredient. Sand is abundant, especially in Egypt, where the desert provides an essentially limitless supply. But pure sand requires temperatures too high for ancient furnaces to reach. So the early glassmakers discovered, or perhaps stumbled upon, the crucial role of what we now call fluxes. Soda lowered the melting point. Sodium carbonate, obtained from natron deposits or from the ashes of certain plants, could be mixed with sand. When heated together, the soda disrupts the silica network, making it easier for the structure to flow and melt. The melting point might drop by hundreds of degrees, bringing glassmaking into the range of achievable furnace temperatures. This was a crucial discovery, perhaps the crucial discovery, that made glassmaking possible. But there was a problem. Glass made with just silica and soda is not stable. It is water-soluble, vulnerable to humidity, prone to degradation. Ancient glassmakers would have noticed that their early glasses could be damaged by water, that they were fragile not just mechanically but chemically. This is where the third crucial ingredient enters the story. Lime stabilized the finished glass. Calcium oxide, typically introduced through limestone or shells, could be added to the mix. Lime acts as a stabilizer, creating a more durable glass that resists dissolution in water, that can survive handling, storage, burial in the ground for millennia. The basic formula, silica, soda, lime, is essentially the same formula still used today for common soda-lime glass, the glass of windows and bottles and jars. Ancient glassmakers, working without chemistry, without microscopes, without scientific theory, discovered through trial and error the same basic recipe that modern science confirms is optimal. Once the technology to make glass was established, even in its early limited form, glass became valuable. Not just as a material, but as a commodity, as an object of trade. Glass ingots were traded between ancient courts. Archaeologists have found evidence of this trade in shipwrecks, in palace storerooms, in diplomatic correspondence on clay tablets. Glass was not made everywhere. The technology was concentrated in a few centers, places with the right materials, the right knowledge, the right concentration of skilled artisans. Raw glass might be made in one location, perhaps in Egypt, where natron and sand were abundant, and then shipped as ingots to other regions. There, local craftspeople would reheat the glass and shape it into beads, vessels, inlay work for furniture or jewelry. Glass became part of early prestige trade networks, moving along the same routes as lapis lazuli from Afghanistan, tin from distant lands, cedarwood from Lebanon, luxury textiles, and precious metals. To receive glass as a gift from another ruler was a sign of status, of diplomatic connection, of participation in the networks of the powerful. Glass appears in royal tombs, in temple offerings, in the archaeological remains of elite residences. It was not yet a material for ordinary people, but a marker of wealth and access to the exotic. Think of how remarkable this is. Within a few centuries of discovering how to make glass, humans had developed trade networks to distribute it across vast distances. The material that began as an accident in a furnace had become valuable enough to ship across seas, to exchange between kings, to incorporate into objects of beauty and prestige. Glass had captured human imagination, had proven itself not just useful but desirable, worth the considerable effort required to produce it. These early glasses were often colored: blue from copper, green from iron, yellow from antimony, deep red from gold. The colors were not always intentional at first. Impurities in the raw materials would tint the glass. But glassmakers learned to control and enhance these colors, to add metallic oxides deliberately, to create specific hues. The brilliant blue of Egyptian glass, achieved through copper compounds, became particularly prized. It resembled lapis lazuli, that precious blue stone imported at great expense from distant Afghanistan. Glass offered a way to achieve similar visual effects more affordably, though it never entirely replaced natural gemstones in value or prestige. As you rest now, imagine that ancient workshop, somewhere in Egypt or Mesopotamia, 5,000 years ago. The furnace glows with heat. An artisan tends it carefully, adding fuel, monitoring temperature through experience and intuition rather than thermometers. Sand and soda and lime, mixed in proportions learned from a master, slowly melt and combine. The glassy substance begins to flow, to glow, to become workable. The artisan takes a metal rod and dips it into the molten glass, gathering a small amount. Working quickly before it cools and hardens, they shape it, perhaps around a core of mud and straw, forming a small vessel or bead. The glass is opaque, colored, not yet the transparent material we think of today. But it is glass nonetheless, made by human hands, the product of observation and experimentation and skill passed down through generations. Outside the workshop, the world is ancient beyond our imagining. Pyramids are new or yet to be built. Writing is newly invented. Bronze is the highest technology. And yet, in this workshop, someone is making glass, creating through a combination of earth, fire, and knowledge something that nature makes only in volcanoes, something that will endure through millennia, that will be found by archaeologists thousands of years later and studied, analyzed, marveled at. From obsidian's volcanic birth to humanity's first fumbling experiments in furnaces, glass had begun its journey through human history. What started as a byproduct, an accident, a curiosity, was becoming something more. Glass was becoming a craft, a trade good, a material with potential that ancient peoples were only beginning to explore. And this was just the beginning. The story of glass was still in its infancy, but already it was clear that this strange, beautiful, difficult material would become important to human civilization in ways that those early artisans could scarcely imagine. Rest now with this image of beginnings, of discovery, of the long, slow process by which humans learned to master what nature had first created. From volcanic glass to furnace-made glass, from accidental byproduct to traded commodity, the journey was underway. For more than 2,000 years after humans first learned to make glass, the material remained precious, limited, the domain of specialists and the possession of elites. The methods of shaping glass were laborious and slow. Early glass was shaped by casting or core forming, techniques that required immense skill and produced only small objects, each one demanding hours or days of careful work. Casting involved creating a mold, perhaps of clay or stone, in the desired shape, then pouring molten glass into it and allowing it to cool. Once solid, the mold would be broken away to reveal the glass object within. This method could produce relatively simple forms, but it was time-consuming. Each mold could typically be used only once. Each piece of glass required the creation of a new mold, the careful preparation of materials, the heating and pouring and cooling and extraction. For complex shapes, casting was simply impractical. The other primary technique was even more elaborate. Core forming used a mud core later scraped out from the interior. Imagine the process. An artisan would first shape a core from a mixture of mud and organic materials like straw or dung, mounted on a metal rod. This core would be shaped into the interior form of the desired vessel, perhaps a small bottle or an unguentarium for precious oils. The core would be dried, sometimes fired to harden it. Then came the delicate work of applying glass. The artisan would heat the core and dip it into molten glass, or wind threads of hot glass around it, building up layers. The glass would be reheated repeatedly to keep it workable, to fuse the layers together, to smooth the surface. Colored glass threads might be wound around the vessel, and then dragged with a tool to create feathered patterns, zigzags, decorative motifs. The work required constant attention to temperature, to timing, to the behavior of the glass as it cooled and stiffened. Once the glass vessel was complete, once it had cooled completely, the difficult task of removing the core would begin. The mud and straw core had to be scraped out, picked out, washed out, leaving behind the hollow glass vessel. It was painstaking work. A single small bottle might represent days of skilled labor. This is why early glass remained expensive, why it was a luxury material, why glass vessels were prized possessions rather than everyday items. But in the 1st century BCE, somewhere in the eastern Mediterranean, perhaps in Syria, perhaps along the Phoenician coast, someone made a discovery that would transform glass forever. Someone discovered that glass could be blown. Glass blowing was invented in the 1st century BCE, and it was nothing short of revolutionary. The technique seems simple in retrospect, but it must have seemed like magic when first discovered. A glassblower would gather molten glass on the end of a hollow metal tube, a blowpipe. Then, by blowing air through the tube, the glassblower could inflate the molten glass like a balloon, expanding it into a bubble, a sphere, a vessel. By controlling the amount of air, the temperature of the glass, the speed of rotation, and by using simple tools to manipulate the expanding form, a skilled glassblower could create a vessel in minutes rather than days. The glass could be blown into molds for more complex shapes, or it could be freely blown and shaped by hand tools while still hot and plastic. Handles could be applied, rims could be shaped, decorations could be added. The possibilities expanded dramatically, and crucially, this made glass vessels cheaper and more varied. The time required to produce a glass object dropped from days to minutes. The skill required was still considerable. Glass blowing is an art that requires years to master, but a single artisan could now produce dozens of vessels in a day rather than laboring over a single piece. The economic implications were profound. Glass, which had been a luxury affordable only to the wealthy, began its transformation into a material accessible to broader segments of society. The timing of this invention was fortuitous. The Roman Republic was transforming into the Roman Empire. Roman power was spreading across the Mediterranean world, into Europe, into North Africa and the Middle East. Roman roads were being built, Roman ships were sailing, Roman trade networks were expanding, and glass spread throughout the Roman world along these networks of commerce and conquest. Glassblowing workshops appeared in cities across the empire. Rome itself, of course, but also Alexandria, Cologne, settlements in Britain and Spain and North Africa. Wherever Roman civilization reached, glass followed. The technology was not kept secret, or if attempts were made to keep it secret, they failed. Knowledge of glassblowing spread rapidly, carried by traveling artisans, by enslaved craftspeople relocated across the empire, by the simple observation and imitation that humans excel at. As production increased and techniques improved, Romans began experimenting with the material itself, seeking to refine its properties. The early glasses, beautiful as they were, had been colored, blues and greens and yellows, the result of impurities in the sand and the other raw materials. But Romans developed clearer, colorless glass. They discovered that the natural color could be eliminated, that glass could be made to approach true transparency. The key discovery was chemical, though Romans would not have understood it in those terms. Manganese dioxide helped remove color tints. When added to the glass mixture, manganese acts as a decolorizer. The iron impurities that typically give glass a greenish or bluish tint are oxidized by the manganese, and the colors effectively cancel each other out. The result is glass that appears colorless, or nearly so, clear enough to see through with minimal distortion. This clearer glass opened new possibilities. For the first time, glass could serve not just as a container or decorative object, but as a medium for viewing, for light, for transparency itself. Early window glass became possible. These were not the flat, smooth panes we know today. Roman window glass was typically cast as rough sheets or blown into cylindrical forms that were then cut and flattened. The resulting panes were uneven, wavy, thick in some places and thin in others, with bubbles and irregularities. But they were transparent enough to admit light, while keeping out wind and rain. Archaeological evidence shows window glass in Roman baths, in villas of the wealthy, in public buildings. The use was not yet universal. Window openings were still often covered with wooden shutters, fabric, or thin sheets of horn or mica. But glass windows represented a new level of comfort and luxury. Imagine a Roman bath complex in winter, with glass windows allowing daylight to flood the warm interior while keeping out the cold. The effect must have been remarkable, almost magical, to be sheltered yet still connected to the light outside. As glassblowing techniques matured and production expanded, glass appeared in nearly all aspects of Roman life. Glass bottles held wine, oil, perfume. Glass cups and bowls graced dining tables, their transparency allowing the color of wine or the contents of a dish to be seen. Glass unguentaria held cosmetics and medicines. Glass beads and jewelry adorned clothing and bodies. Glass tesserae, small glass tiles, were used in mosaics, adding brilliant color, and sometimes even gold leaf encased in glass to decorative floors and walls. Glass funeral urns held the ashes of the dead. Glass lamps illuminated homes. Glass mirrors, backed with metal, allowed Romans to see their reflections with unprecedented clarity. There were glass gaming pieces, glass figurines, glass handles for furniture and doors. The material had penetrated so thoroughly into Roman material culture that some historians sometimes call glass the Roman plastic, drawing a parallel to how plastic pervades modern life. The comparison is apt in more ways than one. Like plastic in the 20th century, glass in the Roman world represented a material that was versatile, relatively inexpensive to produce in quantity, capable of being shaped into nearly any form, and suitable for an enormous range of applications. And like plastic, glass in Roman times represented modernity, innovation, the triumph of human ingenuity over the limitations of traditional materials. Of course, glass never became as cheap or ubiquitous as plastic would become 2 millennia later. Glass production still required fuel, furnaces, skilled labor. A glass vessel was not disposable in the way a plastic container is today. But the trajectory was similar. From precious luxury to common commodity, from rare to familiar, from the possession of elites to something that even ordinary people might own. The spread of glass through Roman society also tells us something about Roman culture itself. The Romans were not particularly interested in keeping technologies secret or restricting their spread. Roman power was based partly on military might, certainly, but also on economic integration, on the spread of Roman material culture, on creating a world where diverse peoples shared common technologies, common goods, common ways of living. Glass fit perfectly into this vision. A merchant in Britannia and a merchant in Syria might speak different languages, worship different gods, eat different foods, but both might drink from similar glass cups. Both might light their homes with glass lamps. Both might store their valuables in glass containers. This standardization, this spread of common material culture, helped bind the empire together in ways that went beyond military conquest or political control. Glass was a small but significant part of this process, a material that carried Roman technical knowledge and aesthetic preferences to the far corners of the known world. As you settle into rest, imagine a glass workshop in ancient Rome, perhaps in the 1st or 2nd century CE. The furnace burns constantly. Keeping it at temperature is easier than heating it up repeatedly. Several glassblowers work at once, each at their station, each with a blowpipe and tools at hand. One gathers molten glass from the furnace, a glowing orange mass on the end of the pipe. They blow gently, and the glass expands, taking on a hollow form. They spin the pipe, using gravity and centrifugal force to shape the growing vessel. They blow again, and the form elongates. A few deft movements with metal tools, with wooden paddles, with shears, and a bottle begins to emerge. Neck narrowing, body swelling, base flattening. The whole process takes perhaps 10 minutes. The finished bottle is placed in an annealing oven to cool slowly, preventing it from cracking from thermal stress. The glassblower is already gathering glass for the next piece. In a single day, this workshop might produce dozens of bottles, bowls, and cups. Some will be sold locally, in Rome's markets and shops. Others will be packed carefully in straw and loaded onto ships or carts, to be traded across the empire. A bottle made in Rome might end up in a merchant's house in Londinium, holding imported olive oil. A cup made in Syria might find its way to a garrison on the Rhine, treasured by a soldier far from home. Glass had completed its first great transformation. Born in nature as obsidian, discovered by accident in ancient furnaces, carefully crafted for millennia as a precious luxury, glass had become, through the Roman innovation of glassblowing and the Roman genius for spreading technology, a common material, an everyday presence, something that touched the lives of millions. The story was far from over. Glass would continue to evolve, to find new applications, to be refined and perfected. But the Roman period established glass as an essential material of human civilization, not a mere curiosity or luxury, but something fundamental, something woven into the fabric of daily life. And this Roman glass, fragments of which are still being excavated from archaeological sites across 3 continents, still carries something of that ancient world. Hold a piece of Roman glass, iridescent now from centuries of burial, its surface weathered into rainbow colors. And you hold a connection to those ancient glassblowers, to their furnaces and their skill, to the empire that spread their craft across the known world. Rest now with the image of transformation, of a material evolving from rare to common, from luxury to everyday utility, from the possession of pharaohs to the simple pleasure of ordinary people drinking wine from a clear glass cup, watching the light pass through, marveling quietly at the transparency, the clarity, the strange beauty of glass. For most of human history, vision was fixed. You saw what your eyes could see, and nothing more. If your eyes were weak, if age had dimmed your sight, if you were born with vision that could not quite focus the world into clarity, there was no remedy. The limits of your eyes were the limits of your perception. The world existed beyond those limits, of course, but it remained invisible, inaccessible, unknowable. Glass changed this. Glass, particularly transparent glass, enabled flat, durable lenses that could bend light in precise, controlled ways. The journey from colored glass vessels to optical lenses was not quick or simple. It required glass that was truly clear, free from the tints and impurities that characterized most ancient glass. It required glass that could be ground and polished to specific curves, to exact shapes, with surfaces smooth enough that light would pass through without excessive scattering or distortion. By the late medieval period, glassmakers in Venice and elsewhere had achieved the necessary quality. They could produce glass clear enough, homogeneous enough, that when shaped into the curved form of a lens, it could focus light predictably. And once such lenses existed, it did not take long for someone to discover that holding a properly shaped piece of glass before the eye could make the blurred world sharp, could bring distant objects closer, could restore the clarity that age or nature had taken away. Spectacles corrected vision for millions of people. The invention of eyeglasses, probably in Italy in the late 13th century, represents one of those technological developments whose impact is difficult to overstate. Before spectacles, someone whose vision deteriorated with age faced increasing limitation. Reading became difficult, then impossible. Fine work, embroidery, manuscript illumination, precision crafts had to be abandoned. Knowledge that existed in written form became inaccessible once one could no longer see the letters clearly. With spectacles, all of this changed. A scholar whose eyes had weakened could continue reading, could continue writing, could extend their productive intellectual life by decades. An artisan could continue their craft. A merchant could continue reading contracts and ledgers. The simple technology of glass lenses, precisely shaped and mounted in frames, gave people back their sight, or at least gave them back enough of it to continue their work, their learning, their participation in the literate world. Corrected eyesight extended productive lifespans in ways that had profound economic and cultural effects. In medieval and Renaissance Europe, literacy was precious and hard-won. To train a scholar, a scribe, a skilled professional took years. To lose that person's ability to read and write when they reached their 40s or 50s, just when their experience and wisdom had accumulated, represented an enormous waste. Spectacles changed this calculation. The investment in education and training could pay dividends for decades longer. Knowledge accumulated over a lifetime did not have to be set aside when eyes grew dim. There was also something quietly revolutionary about spectacles that went beyond their practical utility. They represented the idea that human limitations could be overcome through technology, that what nature had given or taken away could be supplemented, corrected, enhanced. The body was not fixed and immutable, but could be augmented, improved, extended through the application of human ingenuity and craft. But spectacles were only the beginning. Glass lenses could do more than correct vision. They could extend it, could allow humans to see things that no amount of natural visual acuity could ever reveal. Glass lenses made microscopes possible. The microscope emerged in the early 17th century, though its exact origin is disputed. Was it Dutch spectacle makers, experimenting with multiple lenses in combination? Was it Galileo in Italy? The historical record is unclear. But what is clear is that by the 1620s and 1630s, people were using compound lenses to magnify small objects to unprecedented degrees. And what they saw astonished them. Microscopes revealed the microscopic world, a realm that had existed all along, surrounding humanity, within humanity, but completely invisible to the naked eye. A drop of pond water, viewed through a microscope, teemed with tiny creatures, single-celled organisms swimming, feeding, reproducing. These microorganisms, which Antony van Leeuwenhoek called animalcules when he observed them in the 1670s, were unlike anything previously imagined. An entire ecosystem existed in a space smaller than a pinhead, creatures so small that millions could exist unnoticed on a human hand. The microscope revealed that apparently simple materials had hidden complexity. A piece of cork, examined microscopically by Robert Hooke, showed a structure of tiny compartments that Hooke named cells, giving us the term we still use today for the basic units of life. Insects, when magnified, showed intricate structures. Compound eyes made of hundreds of individual facets, wings with delicate vein patterns, mouth parts of bewildering complexity. The small became large, the invisible became visible, and humanity's understanding of nature had to expand to accommodate these revelations. The impact on biology and medicine would be profound, though it took time. The discovery of microorganisms eventually led to germ theory, to the understanding that many diseases were caused by tiny living things too small to see without magnification. This understanding, in turn, revolutionized medicine, hygiene, public health. But none of this would have been possible without glass lenses of sufficient quality to render the microscopic world visible. While some looked at the very small, others turned their attention to the very distant. Glass lenses enabled telescopes. Again, the exact origin is debated. Dutch spectacle makers in the early 1600s? But Galileo Galilei famously refined the telescope and turned it skyward in 1609, and what he saw changed human understanding of the cosmos forever. Telescopes opened the cosmic scale to observation. The moon, which had seemed to the naked eye to be a smooth, perhaps even perfect sphere, revealed itself through Galileo's telescope to be a world. A world with mountains and valleys, with craters and plains, with topography and geography. It was not fundamentally different from Earth, not made of some perfect celestial substance, but a place with features, with terrain. Jupiter, one of the wandering stars that ancient astronomers had tracked across the sky, revealed itself to have moons. 4 of them visible in Galileo's telescope, orbiting the giant planet just as the moon orbits Earth. This was evidence, powerful evidence, that not everything in the heavens circled the Earth. Here were celestial bodies clearly orbiting another center. The Earth-centered cosmos of Ptolemy and Aristotle, which had held sway for nearly 2,000 years, could not easily accommodate this observation. Venus, viewed through the telescope, showed phases like the moon, sometimes a crescent, sometimes gibbous, sometimes nearly full. These phases made sense only if Venus orbited the Sun, not the Earth. The evidence accumulated. The Sun itself, viewed through the telescope with appropriate filters, showed spots, dark blemishes that appeared, moved, and disappeared, suggesting that the Sun rotated and was not the perfect, unchanging celestial object that ancient philosophy had claimed. The telescope, like the microscope, revealed that the universe was more complex, more various, more interesting than humans had imagined. And both instruments, at their core, depended on glass. Glass of high quality, carefully shaped into lenses with precise curves, mounted in tubes that held them at exactly the right distance from each other or from the observer's eye. Glass reshaped biology through the microscope. The discovery of cells, of microorganisms, of the fine structure of tissues and organs, all flowed from the ability to magnify. Naturalists could examine pollen grains, the compound eyes of flies, the fibers of muscles, the capillaries that connected arteries to veins. Each observation added to the growing understanding of how living things were structured, how they functioned, how the visible forms were built up from tiny components working together. Glass reshaped astronomy through the telescope. The discovery of the moons of Jupiter, the phases of Venus, the rings of Saturn, the countless stars of the Milky Way, all visible through telescopes, transformed humanity's conception of its place in the universe. The Earth was not the center of everything, not a special location around which the cosmos arranged itself. It was one planet among several, orbiting one star among billions, in a universe far vaster than anyone had previously imagined. The philosophical and theological implications were profound and contentious. If Earth was not the center, if humans occupied no special position in the cosmos, what did that mean for humanity's sense of significance, for religious doctrines that placed humans at the pinnacle of creation? These were not easy questions, and the debates they sparked sometimes became heated, even dangerous. Galileo himself faced the Inquisition, partly for his telescopic observations and his support of the Copernican model of the solar system. But the observations remained. The evidence was there, visible to anyone who looked through a telescope. The universe revealed through glass lenses could not be unseen. Human understanding had to adjust, had to expand, had to accommodate what glass had made visible. By the 18th and 19th centuries, both microscopes and telescopes had become more sophisticated. Lenses were ground with greater precision. Multiple lenses were combined to correct for aberrations, the colored fringes and distortions that plagued early instruments. Achromatic lenses, which used different types of glass with different refractive properties, could focus different colors of light to the same point, producing sharper, clearer images. Larger telescopes revealed fainter, more distant objects. Nebulae, cloudy patches of light, were seen to be vast collections of stars, galaxies in their own right, each containing billions of stars. The scale of the universe kept expanding with each improvement in telescope technology. More powerful microscopes revealed bacteria, revealed the internal structure of cells, revealed chromosomes during cell division. The mechanisms of heredity, of disease, of development from single cell to complex organism, all became accessible to study through the steadily improving ability to see the very small. And always, at the heart of these instruments, was glass. Glass lenses gathering light, bending it, focusing it, allowing human eyes to perceive what they could never perceive alone. Humans could now see far beyond unaided sight, in both directions, into the minute and into the immense, into the hidden structure of matter and into the distant reaches of space. This represents a profound transformation in human capability. For hundreds of thousands of years, humans had been limited to what their natural senses could perceive. The invention of tools extended human physical capabilities, axes and plows and wheels and ships. But glass lenses extended human perception itself. They allowed humans to gather information that would otherwise be completely inaccessible. They opened new realms of investigation, new domains of knowledge, new frontiers to explore. As you rest now, consider the magnitude of this gift that glass provided. A scholar whose vision fails can read again through spectacles, can continue learning, can continue contributing. A naturalist can peer into a drop of water and discover entire worlds of living things. An astronomer can point a tube of glass lenses skyward and see moons circling Jupiter, can watch the phases of Venus, can count stars invisible to the naked eye. The world is larger than we thought, and smaller, more complex than we imagined, more populous, more varied. And glass showed us this. Glass, that strange material neither solid nor liquid, that frozen disorder of atoms, became the medium through which humans transcended the limitations of their eyes, through which they learned to see beyond the visible, to know beyond the previously knowable. In the darkness before sleep, imagine Galileo on a rooftop in Padua, adjusting his telescope, looking at Jupiter, and seeing for the first time those 4 points of light arranged in a line near the bright planet. Imagine his mind working, calculating positions, returning night after night, documenting the moon's motion, realizing what he was seeing. Imagine Leeuwenhoek in Delft, holding one of his simple but powerful single-lens microscopes close to his eye, examining a sample of water from the canal, and seeing movement, seeing life, seeing creatures that no human had ever seen before. These were moments of revelation, made possible by glass. And they were only the beginning. The story of glass and human vision would continue, would lead to cameras and projectors, to fiber optics and laser surgery, to instruments that extend human perception in ways still being invented. But the foundation was laid in those early centuries, when craftspeople learned to make glass clear enough and pure enough to shape into lenses, and curious minds learned to use those lenses to see the previously invisible. Rest now with the thought of sight extended, of perception enhanced, of human curiosity, finding in glass the tool it needed to explore beyond the boundaries that nature had set. Glass changed how humans see, and in doing so, changed what humans could know, and in changing what humans could know, changed humanity itself. The universe, both vast and minute, waited to be seen. Glass made the seeing possible. For thousands of years, humans used glass to look through windows, lenses, spectacles, telescopes. Glass was transparent, and transparency was its gift to humanity. Light passed through glass on its way to somewhere else, on its way to an eye or an instrument or a room. Glass was the medium through which light traveled, but the journey was always short. The thickness of a window pane, the length of a lens, perhaps a few inches at most. But in the 20th century, scientists and engineers discovered something remarkable. They discovered that glass could do more than simply allow light to pass through it. Glass could guide light, could hold it, could carry it across vast distances without letting it escape. They discovered that hair-thin glass fibers can guide light along paths that could bend and curve, that could stretch not for inches, but for miles, for hundreds of miles, eventually for thousands of miles. This discovery would transform global communication, would become the foundation of the modern internet, would make it possible for you to read these words, to watch videos, to communicate instantaneously with someone on the other side of the planet. But the journey to this discovery required solving problems that seemed, at first, nearly impossible. The basic principle behind optical fibers is elegant. Fibers use a high-index core and low-index cladding. Imagine a strand of glass, so thin that it's nearly invisible to the naked eye, far thinner than a human hair in some cases. This fiber has a structure. At its center is a core, made of glass with a particular refractive index, a measure of how much that glass bends light. Surrounding this core is a layer of cladding, also glass, but with a slightly lower refractive index. This difference in refractive index is crucial. When light travels from a material with a higher refractive index to one with a lower refractive index, and when it hits the boundary at a shallow enough angle, something remarkable happens. The light does not pass through into the second material. Instead, it bounces back, reflects completely, as if the boundary were a perfect mirror. This phenomenon is called total internal reflection, and it traps light in the core of the optical fiber. Think of light entering one end of the fiber. It travels down the core, and whenever it encounters the boundary between the core and the cladding, it reflects back into the core rather than escaping into the cladding or out into the surrounding air. The light bounces back and forth as it travels, zigzagging down the length of the fiber, but never escaping, guided by the structure of the glass itself. The fiber can bend, can curve, can loop, and the light follows the path, trapped by total internal reflection, traveling onward. This is how optical fibers work in principle. The reality of making them work in practice required solving extraordinary technical challenges. Light does not travel through glass at the speed it travels through vacuum. In vacuum, light travels at approximately 186,000 miles per second, the cosmic speed limit. In glass, light slows down. Light travels about 125,000 miles per second in fiber, roughly 2/3 the speed of light in vacuum. This is still extraordinarily fast. In 1 second, light in an optical fiber could circle the Earth more than 5 times. But it's slower than in empty space, slowed by the interaction of light with the atoms of the glass. But speed was not the main challenge. The main challenge was loss. Early attempts to use glass fibers to carry light over long distances failed, because the glass simply was not transparent enough. This might seem strange. Glass is transparent, after all. You can look through a window and see clearly. But transparency over a few millimeters, or even a few centimeters, is very different from transparency over kilometers. Every material absorbs at least some light. Even the clearest window glass, if made thick enough, would eventually absorb enough light that you couldn't see through it. The same is true for optical fibers. As light travels through the fiber, some of it is absorbed by impurities in the glass, some is scattered by tiny irregularities in the glass structure. Over short distances, these losses are negligible. Over long distances, they become overwhelming. The light entering one end of a long fiber would be almost completely absorbed before reaching the other end. For optical fibers to be practical for communication, the glass had to be extraordinarily pure, more pure than almost any other manufactured material. Ultra-pure glass can be more transparent than water. This is a startling statement. Water seems perfectly transparent. Look through a glass of water and you see clearly. But water actually absorbs light significantly over long distances. Deep in the ocean, light from the surface is absorbed within a few hundred feet at most. The purest optical fiberglass is more transparent than that, dramatically so. The breakthrough came in 1970, when Corning developed low-loss optical fiber. A team of researchers at Corning Glass Works, led by Robert Maurer, Donald Keck, and Peter Schultz, succeeded in creating optical fiber with loss low enough that signals could travel useful distances without needing to be amplified. The fiber they developed had a loss of about 20 decibels per kilometer, which sounds technical, but meant that light could travel a kilometer and still retain about 1% of its intensity. This doesn't sound like much, but it was a dramatic improvement over previous attempts, and it was enough to make practical systems possible. Within a few years, Corning and others pushed the technology further, developing fibers with even lower losses, eventually achieving losses below 0.2 decibels per kilometer. At this level of transparency, light could travel tens of kilometers, even hundreds of kilometers, before needing amplification. This made long-distance optical communication practical. But why use light to communicate in the first place? What advantage did optical fibers offer over the copper wires that had carried telephone and telegraph signals for more than a century? The answer lies in capacity. Optical fibers enabled high-capacity data transmission at a scale that copper could never match. The amount of information you can send through any communication channel depends on the frequency of the signal. Higher frequencies allow more information to be encoded. Radio waves, which had been used for wireless communication, operate at relatively low frequencies. Electrical signals in copper wires operate at even lower frequencies by comparison. But light oscillates at extraordinarily high frequencies, hundreds of trillions of times per second. This means that a light signal can carry vastly more information than an electrical signal in a wire or a radio wave through the air. A single optical fiber, thinner than a human hair, can carry thousands of phone calls simultaneously, or can transmit data at rates measured in gigabits or even terabits per second. One fiber can carry more information than hundreds or thousands of copper wires. Moreover, optical fibers are immune to electromagnetic interference. Copper wires can pick up stray electromagnetic signals, causing noise and degrading the signal. Glass fibers, carrying light instead of electricity, are unaffected by electromagnetic fields. They can be run alongside power lines, through electrically noisy environments, without picking up interference. And glass fibers are lightweight, flexible, durable. They don't corrode. They don't conduct electricity, so there's no risk of electrical shorts or sparks. They can be made from silica, which is essentially sand, one of the most abundant materials on Earth, rather than copper, which is a relatively scarce metal that must be mined and refined. All of these advantages meant that once the technology matured, once the manufacturing processes were refined and costs came down, optical fibers began replacing copper for long-distance communication. By the 1980s and 1990s, telecommunications companies were laying optical fiber cables across continents and beneath oceans. Glass fibers became the backbone of the internet, the physical infrastructure that makes global digital communication possible. Today, vast networks of optical fiber span the world. Cables lie on the ocean floor, connecting continents, carrying the data that makes up international phone calls, streaming videos, financial transactions, emails, web pages, everything that constitutes the internet. There are hundreds of thousands of miles of undersea fiber-optic cable alone, and millions of miles of fiber in terrestrial networks. Modern global communication relies on glass. Not the glass of windows or lenses, but glass drawn into fibers so thin and so pure that light can travel through them across oceans, carrying information at nearly incomprehensible speeds. Consider what this means. When you make a video call to someone on another continent, your voice and image are converted into digital data, ones and zeros represented by the presence or absence of light pulses. These pulses travel through optical fibers, perhaps buried under streets, perhaps spanning the ocean floor, bouncing back and forth within the glass core through total internal reflection, traveling at 125,000 miles per second. The light might travel thousands of miles, might pass through dozens of amplifiers and switches, but it remains guided by glass, trapped by the boundary between core and cladding, following the path that engineers have laid out. And it all happens so quickly that the delay is barely perceptible. Light traveling through fiber can cross the Atlantic Ocean in about 60 milliseconds, less than a tenth of a second. The entire round trip, accounting for the time it takes to convert signals, route them, process them, is often less than a quarter of a second. You speak, and someone across the ocean hears you almost instantly, as if distance had collapsed, as if the ocean between you had ceased to matter. This is the gift that optical fiber has given to the modern world. The ability to communicate as if distance were irrelevant, to access information stored anywhere as if it were stored locally, to participate in global networks of commerce and culture and knowledge without regard to physical location. And it's all made possible by glass. Glass refined to a degree of purity that would have been unimaginable to ancient glassmakers. Glass drawn into fibers of precisely controlled diameter and structure. Glass engineered at the molecular level to minimize absorption and scattering. Glass that has become, in some sense, More transparent than empty space would be if empty space could scatter light the way matter does. The scientists and engineers who developed optical fiber technology had to solve problems that touched on fundamental physics, on materials science, on chemistry and engineering. They had to understand light and how it interacts with matter. They had to develop manufacturing processes that could create glass of unprecedented purity. They had to design systems that could encode information onto light pulses, that could amplify weak signals without distorting them, that could route signals through complex networks. Each of these challenges required innovation, persistence, the accumulation of knowledge across decades and across disciplines. The optical fiber networks that now span the world represent one of humanity's great engineering achievements, comparable to the construction of railroads or highways or power grids in their scope and their impact on society. As you rest now, think about the invisible rivers of light flowing through glass beneath oceans, beneath streets, through the walls of buildings. Think about information traveling at an appreciable fraction of the speed of light, guided by the same material that humans have been shaping for 5,000 years. The same material that began as volcanic glass used for cutting tools and evolved into windows, lenses, and now into the carrier of nearly all long-distance communication. Glass has come so far from its origins. From obsidian blades to fiber-optic cables, from colored beads to strands of ultra-pure silica that carry the world's data, glass has been repeatedly reimagined, its properties understood more deeply, its potential pushed further. And perhaps the most remarkable thing is that the fundamental material is still, at its core, the same disordered, amorphous solid that has always puzzled physicists. The atoms in an optical fiber are arranged in the same liquid-like disorder as the atoms in ancient Roman glass. The fiber is still glass, still that strange substance that is neither quite solid nor quite liquid, still that frozen moment between order and chaos. But now, in addition to all its other properties, glass has learned to carry light across the world, to guide photons along paths thousands of miles long, to make possible the instantaneous global communication that defines the modern age. Light has learned to travel through glass not just for inches, but for continents, and in learning this, light has brought the world closer together, has made distance less important, has changed what it means for humans to communicate, to share knowledge, to remain connected across the vast spaces of the Earth. Rest now with the thought of light traveling through glass, pulsing with information, crossing oceans in fractions of a second, guided by total internal reflection, by the careful engineering of refractive indices, by the extraordinary purity of modern optical fiber. Rest knowing that glass, ancient and familiar, has become the medium of the modern world, the material through which our digital age flows. The glass that changed how humans see has now changed how humans connect. And the story continues still. We have spoken of glass as if it were a single substance, a single material with fixed properties. But this is a simplification, a convenient fiction. The truth is far more interesting, far more versatile. Glass is not one material, but a vast family of materials, each with different properties, each optimized for different purposes. Glass composition is highly adaptable, capable of being adjusted, tuned, customized to meet specific needs in ways that few other materials can match. The basic recipe for glass, silica, soda, lime, produces what we call soda-lime glass, the glass of windows and bottles and drinking vessels. This is the most common type of glass, the glass that has been made in vast quantities for centuries. But it is only the beginning. By changing the proportions of these ingredients, by adding other elements and compounds, glassmakers can alter the properties of glass dramatically. Additives can tune color and refractive index. Want red glass? Add gold or selenium or cadmium sulfide. Want deep blue? Add cobalt oxide. Green can come from iron or chromium. Purple from manganese or neodymium. The colors of stained glass windows, the tinted glass of bottles, the colored glass of art and decoration, all come from deliberately added metal oxides and compounds that absorb certain wavelengths of light, while transmitting others. But color is only the most visible property that additives can control. The refractive index, how much the glass bends light, can be adjusted by adding lead oxide, which increases the refractive index significantly. This creates what's called lead glass or crystal, prized for its brilliance and its ability to disperse light into rainbow colors, which is why fine glassware and chandeliers often use lead glass. The same high refractive index makes lead glass useful for optical applications where strong light-bending power is needed. Additives can tune toughness and thermal resistance as well. Standard soda-lime glass is relatively fragile and sensitive to temperature change. Heat one part of a glass object while another part remains cool, and thermal stresses can cause the glass to crack or shatter. But add boron oxide to the glass mixture, and something changes. The resulting borosilicate glass, which we'll explore more in a moment, can withstand much larger temperature variations without breaking. Add certain elements, use certain heat treatments, and you can create glass that is far tougher than ordinary glass, more resistant to impact and scratching. The process of tempering, heating glass and then cooling it rapidly, creates surface compression that makes the glass several times stronger than untreated glass. When tempered glass does finally break, it shatters into small, relatively harmless pieces rather than large, dangerous shards, which is why it's used for car windows and shower doors. But perhaps one of the most elegant examples of engineering glass for specific properties is the technology behind the glass in your smartphone. That smooth, tough screen that you touch hundreds of times a day, that survives being carried in pockets and bags, that resists the scratches and impacts of daily use. That glass is a marvel of materials engineering. Chemically strengthened smartphone glass uses ion exchange, a process that sounds like alchemy, but is actually sophisticated chemistry. Here is how it works. The glass is made with a specific composition that includes sodium ions, sodium atoms that have lost an electron and carry a positive charge. These sodium ions are part of the glass structure, sitting in spaces within the disordered network of silicon and oxygen atoms. The glass is then immersed in a hot bath of molten potassium salt, heated to temperatures around 400 degrees Celsius. At this temperature, something remarkable happens. Sodium ions are replaced by potassium ions at the surface of the glass. The potassium ions from the molten salt diffuse into the glass, while sodium ions from the glass diffuse out into the salt. The two types of ions trade places, hence ion exchange. But there's a crucial difference. Potassium ions are larger than sodium ions. A potassium ion, trying to fit into the space that a sodium ion previously occupied, is like trying to put a large marble into a space designed for a small marble. The result? The surface of the glass becomes crowded, compressed. This creates compressive stress that resists cracking. Cracks in glass typically start at the surface, where tiny flaws or scratches concentrate stress. But if the surface is already under compression, if it's being squeezed inward by the crowding of those oversized potassium ions, then additional stress from impacts or bending has to first overcome that compression before a crack can form and propagate. This makes the glass dramatically stronger. Chemically strengthened glass can be several times more resistant to breakage than ordinary glass of the same thickness. It can be made thinner while maintaining strength, which is crucial for smartphones and tablets, where every fraction of a millimeter of thickness matters. The ion exchange process happens only at the surface, to a depth of tens or hundreds of micrometers. But this is exactly where strength is needed most, because this is where cracks begin. The technology is a beautiful example of engineering at the atomic level. By understanding how ions behave in glass, by controlling diffusion processes, by deliberately creating stress patterns, materials scientists have created glass that can survive the daily abuse of being carried in a pocket, dropped occasionally, cleaned repeatedly, and still maintain its smooth, scratch-resistant surface. Now let us consider glass compositions optimized for very different purposes. For certain optical and scientific applications, even the small amount of color and absorption present in ordinary glass is too much. For work with ultraviolet light, or with infrared light, special glass is needed. Fused silica transmits UV and infrared light far better than ordinary glass does. Fused silica, sometimes called fused quartz, is glass made from pure silicon dioxide, essentially pure sand, melted at extremely high temperatures and cooled into glass without adding soda or lime or other ingredients. Because it lacks these additives, and because the silicon dioxide itself is so pure, fused silica is transparent not just to visible light, but also to shorter wavelengths in the ultraviolet and longer wavelengths in the infrared. This makes fused silica essential for UV lamps, for optical systems that work with UV light for lithography in semiconductor manufacturing, for infrared spectroscopy, for fiber optics designed for certain wavelengths. Fused silica is also extremely resistant to thermal shock. You can heat it red hot and plunge it into cold water without it cracking, and it has a very low coefficient of thermal expansion, meaning it barely changes size when temperature changes. This thermal stability becomes even more critical in certain precision applications. Consider a telescope mirror that must maintain its exact shape as temperature varies throughout the night. Consider optical instruments in spacecraft that experience extreme temperature swings between sunlight and shadow. For these applications, even fused silica's low thermal expansion is not quite enough. Engineers needed something even more stable. The answer came from a surprising direction. Ultra-low expansion glass ceramics resist temperature change to an extraordinary degree. These materials are technically not pure glass, but a composite of glass and tiny ceramic crystals, carefully engineered to have coefficients of thermal expansion near zero. The glass ceramic can be heated or cooled through a wide temperature range, and it will barely change dimensions at all. The most famous of these materials is probably Zirida, developed by Schott, which has been used for telescope mirrors, for optical benches in precision instruments, for applications where even the tiniest thermal distortion cannot be tolerated. The material starts as glass, but through careful heat treatment, tiny crystals are grown throughout the glass matrix. The glass and the crystals have opposite thermal expansion behaviors. One wants to expand when heated, the other wants to contract. And in the right proportion, they cancel each other out almost perfectly. The result is a material that maintains its shape with extraordinary precision across temperature changes. This allows astronomers to build telescope mirrors that perform consistently whether the night is warm or cold. It allows scientists to build optical instruments that don't need constant recalibration as laboratory temperature fluctuates. For more everyday applications, but still requiring special properties, there is borosilicate glass. Borosilicate glass resists heat and chemicals better than ordinary soda-lime glass. You may know it by its most famous brand name, Pyrex, though the composition sold under that name has varied over time and by region. Borosilicate glass includes boron oxide in its composition, which changes the glass structure in ways that reduce thermal expansion. The glass expands much less when heated than ordinary glass does, which means it can withstand rapid temperature changes without breaking. This is why borosilicate glass is used for cookware, for laboratory glassware, for applications where glass might be heated quickly or where hot liquids might be poured into it. Borosilicate glass also has excellent chemical resistance. It is not attacked by most acids or bases, which makes it ideal for laboratory equipment, for chemical processing, for containers that must hold aggressive chemicals. Scientists around the world perform experiments in borosilicate beakers and flasks, trusting that the glass will not react with or be dissolved by the chemicals inside. All of these specialized glasses, chemically strengthened smartphone glass, fused silica for UV optics, ultra-low expansion glass ceramics for telescopes, borosilicate for labs and kitchens, demonstrate a fundamental truth. Glass can be precisely engineered for purpose. It is not a take-it-or-leave-it material with fixed properties, but a flexible platform for innovation. Materials scientists think of glass composition space as a vast multidimensional landscape. Each element that can be added, each possible heat treatment, each manufacturing process, represents a dimension in this space. Different points in this space correspond to different glass compositions with different properties. And humans have been exploring this space, sometimes systematically, but often through experimentation and serendipity, for thousands of years. Every new glass composition represents a discovery, a finding that this particular combination of elements, prepared in this particular way, produces glass with useful properties. Some of these discoveries are dramatic breakthroughs, like the low-loss optical fiber that enabled global communication. Others are incremental improvements, fine-tuning existing glasses to be slightly better for their intended purpose. But all of them represent the human drive to understand and control materials, to shape the physical world to meet human needs and desires. Glass, in its extraordinary diversity, stands as a testament to this drive. From colored glass for art and beauty, to optical glass for science and vision, to ultra-pure glass for communication, to chemically strengthened glass for durability, to thermally stable glass for precision. Each is glass, each shares that fundamental amorphous structure, but each is optimized, tuned, engineered. As you settle into rest, think about the glass objects around you. Each one might be taken for granted, might seem like simple, ordinary glass. But each likely represents specific choices about composition, about manufacturing, about engineering. The window glass is formulated to be inexpensive and adequately durable. The screen of your phone contains ions exchanged at its surface for strength. Laboratory glassware is borosilicate for chemical and heat resistance. Optical fibers in cables are ultra-pure silica for transparency. Each glass, precisely chosen for its purpose. This adaptability, this tunability, is part of what makes glass so valuable, so versatile, so persistent across human history. As needs change, as new applications emerge, glass changes with them. New compositions are developed, new processes invented, new properties discovered. The material that began as accidental puddles in ancient furnaces has become a platform for sophisticated engineering, a canvas for chemical creativity, a substrate for innovation. Glass is not one thing but many things, not fixed but flexible, not simple but endlessly complex. Rest now knowing that even the most ordinary glass object represents thousands of years of accumulated knowledge, represents deliberate choices about composition and process, represents human understanding of how atoms can be arranged to create materials with the properties we need. Glass bends to human while maintaining its essential nature, that disordered, amorphous, paradoxical structure that physicists still work to fully understand. Engineered yet mysterious, designed yet fundamentally puzzling, glass continues to serve humanity while keeping its deepest secrets. The material is a mirror, in more ways than one, reflecting not just light but human ingenuity, human curiosity, human persistence in understanding and shaping the physical world. Light and glass have always had an intimate relationship. Glass is defined by its transparency, by the way light passes through it. But for the most sophisticated optical applications, for cameras and microscopes, for telescopes and laser systems, for the instruments that allow us to see and measure and image with extraordinary precision, simply being transparent is not enough. The glass must control light with exactness that approaches the limits of what physics allows. Consider what happens when white light passes through an ordinary glass lens. White light is not a single thing, but a mixture of colors, a mixture of different wavelengths. Red light has a longer wavelength, blue light a shorter wavelength, and all the colors of the rainbow lie in between. When light enters glass and bends, refracts, at the surface, different wavelengths bend by slightly different amounts. Blue light bends more than red light. This means that a simple lens will focus different colors at slightly different points. The result is chromatic aberration, color fringing, a blurring of the image, a halo of colors around bright objects. For casual purposes, this might not matter much. But for precision optics, for applications where sharpness and accuracy are crucial, chromatic aberration is unacceptable. And so, some optical glasses minimize chromatic aberration through careful composition. These are the low dispersion glasses that improve image sharpness. Dispersion is the technical term for how much different wavelengths of light are separated when passing through glass. High dispersion glass spreads colors apart significantly. Low dispersion glass, also called extra low dispersion or ED glass, keeps colors together more closely, reducing the chromatic aberration problem. Low dispersion glasses are made by adding specific elements to the glass composition. Fluorite, special rare earth elements, carefully chosen combinations that alter how the glass interacts with different wavelengths. These glasses are expensive to produce, more difficult to work with than ordinary optical glass, but their performance is superior. High-end camera lenses, astronomical telescopes, precision optical instruments, all rely on low dispersion glass elements to achieve the sharpness and color accuracy that professionals demand. Often, low dispersion glass is combined with ordinary glass in what's called an achromatic doublet. Two lenses made of different types of glass, designed so that their dispersion effects partially cancel each other out. The combination brings different colors to focus at nearly the same point, dramatically reducing chromatic aberration. This technique, developed centuries ago, is still fundamental to modern lens design. But glass can control light in ways beyond simple refraction at its surfaces. Gradient index lenses, or GRIN lenses, bend light internally through a clever variation in the glass itself. In an ordinary lens, the refractive index is uniform throughout. The glass is the same everywhere. But in a GRIN lens, the composition varies gradually from the center to the edge, creating a smooth gradient in refractive index. This gradient causes light to bend continuously as it passes through the lens, following a curved path rather than traveling in a straight line and bending only at the surfaces. The effect is that a flat, parallel-sided piece of GRIN glass can act as a lens, focusing or defocusing light without requiring curved surfaces. This is useful for applications where curved surfaces are difficult or undesirable. For instance, in endoscopes, those thin tubes that doctors use to look inside the body. A GRIN lens can be small, cylindrical, flat-ended, yet still focus light to create an image. Creating GRIN lenses requires extraordinary control over glass composition. The refractive index must vary precisely, smoothly, reproducibly. This is typically achieved through ion exchange or diffusion processes, where certain ions are allowed to diffuse into the glass in controlled patterns, altering the local composition, and thus the local refractive index. It is a delicate process, a testament to how precisely modern glassmaking can control material properties. Even the finest glass lens, perfectly shaped and composed of ideal optical glass, faces another challenge. When light encounters the boundary between air and glass, some of it reflects rather than transmitting through. This reflection might be only 4 or 5% of the light at each surface, but in a complex optical system with many glass elements, a camera lens might have 10 or 15 individual glass elements. These small reflections add up. Light bounces between surfaces, creating internal reflections, reducing contrast, creating ghost images and flare. The solution is anti-reflection coatings that reduce glare and unwanted reflections. These are thin films, deposited on the glass surface, often only a few hundred nanometers thick, less than the wavelength of visible light. The coatings work through interference. Light reflecting from the top surface of the coating interferes destructively with light reflecting from the bottom surface of the coating, cancelling out the reflection. The effect can be dramatic. An uncoated glass surface might reflect 4% of incident light. A properly designed anti-reflection coating can reduce this to less than 1%, sometimes to just a few tenths of a percent. In a complex lens system, this means much more light reaches the sensor or film. Much less light bounces around internally, creating artifacts. The result is brighter images, higher contrast, better color saturation, cleaner rendering of bright light sources. Modern high-performance optics almost always use multi-layer anti-reflection coatings. Multiple thin films stacked together, each designed to reduce reflection at specific wavelengths. The coating might have 5 or 10, or even more layers, each precisely controlled in thickness and composition. Looking at a coated lens, you might see a subtle purple or green tint. This is the residual reflection that the coating hasn't eliminated, typically chosen to be in wavelengths where the eye is less sensitive. For certain scientific applications, controlling the shape and smoothness of glass surfaces becomes critical at scales that seem almost incomprehensible. Optical flats are polished flatter than visible wavelengths of light. A visible wavelength is on the order of half a micrometer, about 500 nanometers. High-quality optical flats can be polished to deviations of just a few nanometers, a small fraction of a wavelength, over their entire surface. These surfaces are so flat that when two optical flats are placed in contact, they can ring together, adhere through molecular forces, and become very difficult to separate. Optical flats are used as calibration standards to measure the flatness of other surfaces to test optical systems. They represent the pinnacle of mechanical precision in glassworking, achieved through careful grinding and polishing with progressively finer abrasives, with constant measurement and adjustment. Glass can also manipulate light through internal reflection in ways that don't require extreme flatness. Glass prisms fold optical paths via internal reflection, redirecting light at precise angles. A prism can split white light into its component colors, each wavelength bending by a different amount. This is how Newton demonstrated that white light is composed of colors. But prisms also serve practical functions in optical instruments. A right-angle prism can turn light by 90 degrees, redirecting an optical path. A roof prism can flip an image while redirecting it. Binoculars use prisms to fold the optical path, making the instrument more compact while also correcting the inverted image that the objective lenses produce. Prism-based systems can be more compact and more robust than mirror-based systems for many applications, and the precise angles of well-made prisms ensure accurate light direction. Sometimes the goal is not to control the direction or focus of light, but simply to reduce its intensity. Neutral density filters reduce light intensity without changing its color balance. These are pieces of glass that absorb light uniformly across the visible spectrum, dimming the light without tinting it. They're essential for photography when bright conditions would otherwise overexpose the image, or when a photographer wants to use a slow shutter speed or wide aperture in bright light. They're used in scientific instruments to prevent detector saturation, to bring intense light sources into a measurable range. Neutral density filters can be made by incorporating fine metal particles or other absorbing materials into the glass, or by coating the glass with partially reflective metallic films. The challenge is achieving neutral absorption, reducing all colors equally, which requires careful selection of absorbing materials and precise control of concentration or coating thickness. Related but distinct are filters that absorb selectively by wavelength. Heat-absorbing glass blocks infrared radiation while transmitting visible light. This is useful in situations where intense light sources produce substantial heat. For instance, in projection systems, where a powerful lamp illuminates a slide or film. Without heat-absorbing glass, the infrared radiation from the lamp would heat and potentially damage the material being projected. Heat-absorbing glass, incorporating iron or other elements that absorb in the infrared, removes the heat while allowing the visible light to pass through. Some glasses even respond dynamically to light. Photochromic glass darkens in sunlight, providing automatic adjustment to changing light conditions. You may be familiar with photochromic eyeglasses that darken outdoors and clear up indoors. The effect comes from silver halide crystals embedded in the glass. When exposed to ultraviolet light, which is present in sunlight but largely blocked by building windows, the silver ions in these crystals undergo a reversible chemical change, forming metallic silver that absorbs visible light and darkens the glass. Remove the UV light, and the process reverses. The metallic silver converts back to silver ions. The crystals become transparent again, and the glass clears. The transformation is gradual, taking minutes to fully darken or clear, giving the characteristic slow response of photochromic lenses. The technology is elegant, a purely passive, reversible response to UV light, requiring no power source no electronic control, just clever chemistry frozen into glass. All of these technologies, low-dispersion glasses, grin lenses, anti-reflection coatings, optical flats, prisms, filters, photochromic glass, demonstrate the extraordinary precision with which modern optical engineering can control light using glass. And the truth is that glass optics shape nearly all modern imaging. From the camera in your phone to the largest telescopes on Earth, from microscopes examining cells to endoscopes examining internal organs, from projectors to copiers to fiber-optic communication systems, nearly every technology that forms, transmits, or manipulates images relies fundamentally on glass optics. Consider a modern camera lens. It might contain 15 or more individual glass elements, each precisely ground and polished, each made of glass chosen for specific optical properties. Perhaps low-dispersion glass for some elements, high refractive index glass for others. Each surface is coated with multi-layer anti-reflection coatings. The elements are assembled with micrometer precision, aligned so that their optical centers line up perfectly. The result is a device that can form sharp, accurate images across a wide field of view, under varying light conditions, with minimal aberrations or artifacts. Or consider a modern microscope objective, one of the most complex and precise optical devices ever made. A high-performance objective might contain 20 or more glass elements, including some made of exotic glasses, or even crystal materials, all working together to form a magnified image with minimal aberration. The design requires sophisticated computer modeling, the manufacturing requires extraordinary precision, and the result is an instrument that can resolve details smaller than the wavelength of light through clever optical tricks. Even your smartphone, with its tiny camera, contains aspherical glass lenses. Lenses whose surfaces are not simple spherical curves, but more complex shapes, designed to reduce aberrations in compact form. These lenses are molded rather than ground, pressed into shape while the glass is hot, but they still require precise control of glass composition, temperature, and pressure to achieve the necessary optical quality. As you rest now, think about the light around you. If you're reading by lamplight, that light has perhaps passed through glass in the lamp itself. If you're looking at a screen, the light forming the image passes through glass or glass-like materials. If you wear glasses, light is being bent by precisely shaped lenses to correct your vision. If there are windows, light from outside is passing through glass to illuminate your space. All of this light is being controlled, bent, filtered, focused, transmitted by glass that has been engineered with extraordinary care. The glass is not just transparent, but precisely transparent. Not just refractive, but precisely refractive in controlled ways. The surfaces are not just smooth, but smooth to within nanometers. The composition is not just glass, but specific formulations chosen for exact optical properties. This level of control, this precision, represents centuries of accumulated knowledge about light and glass and how they interact. It represents the work of lens grinders and opticians, of physicists and chemists, of engineers and manufacturers. It represents both deep theoretical understanding and practical craftsperson's knowledge. The understanding of how glass behaves, how it can be shaped and coated and combined to achieve desired effects. And yet, for all this sophistication, we still don't fully understand glass itself at the most fundamental level. We can engineer it precisely, can predict its optical properties with great accuracy, can manufacture it with extraordinary quality control. But that fundamental question, what is glass really at the atomic level, remains incompletely answered. This is the beautiful paradox. We can control glass precisely enough to polish surfaces flat to within a few nanometers, to create coatings that manipulate light at the wavelength scale, to design lenses that correct for aberrations smaller than the human eye can detect. Yet the material itself, in its deepest nature, remains somewhat mysterious. Rest now with the thought of light, precisely controlled, passing through glass that has been engineered with extraordinary care. Think of photons, particles of light, encountering surfaces polished to near-perfect flatness, passing through glass of precisely tuned refractive index, perhaps bouncing off coatings designed to manipulate them in specific ways, finally forming images, or carrying information, or simply illuminating your world. Glass has become humanity's tool for controlling light, for shaping and directing and filtering the photons that allow us to see, to image, to communicate. From simple transparency to sophisticated optical engineering, glass has evolved alongside human understanding of light itself. And the story continues. New optical glasses are still being developed, new coatings designed, new techniques for controlling light invented. Glass, ancient and familiar, remains at the frontier of optical technology, still essential, still irreplaceable, still the material through which we shape light to our purposes. We have already spoken of optical fibers, those hair-thin strands of ultra-pure glass that guide light across vast distances through total internal reflection. But the story of optical fiber has continued to evolve, driven by an insatiable demand for more capacity, more speed, more information flowing through the world's communication networks. Engineers and scientists have pushed fiber technology far beyond those early simple designs, creating exotic structures and employing sophisticated techniques that transform what glass can do. One of the most remarkable innovations is the photonic crystal fiber, a structure so intricate, so precisely engineered, that it seems almost impossible. Photonic crystal fibers contain patterned air holes running along their entire length. Imagine looking at the end of such a fiber under a microscope. You would see not just a simple core and cladding, but an elaborate pattern, perhaps hundreds of tiny air holes arranged in a regular lattice, surrounding a central region where light travels. These air holes, each perhaps a few micrometers in diameter, run parallel along the entire fiber length, which might be kilometers long. Creating such structures requires extraordinary manufacturing precision. The fiber is typically made by stacking glass tubes and rods in a precise pattern to form what's called a preform, then heating and drawing this preform down to fiber dimensions, reducing it by a factor of 100 or more while maintaining the pattern of holes. Why go to such trouble? Because these guide light in ways ordinary fibers cannot. The periodic structure of air holes creates what physicists call a photonic bandgap. Certain wavelengths of light simply cannot propagate through the holy region. So light is confined to the core, not by total internal reflection, but by this photonic bandgap effect. This allows for fiber designs that would be impossible with conventional approaches. Photonic crystal fibers can guide light in hollow cores. The light travels mostly through air rather than glass, which means lower loss and less distortion for certain applications. They can be designed to have unusual dispersion properties, to maintain single-mode operation over very wide wavelength ranges, to generate unusual nonlinear optical effects. They represent a frontier in fiber technology, where the precise structure of the glass and air pattern gives unprecedented control over how light behaves. But even in conventional solid-core fibers, engineers have developed sophisticated ways to manipulate light. Fiber Bragg gratings are written into glass fibers, creating structures that reflect specific wavelengths while transmitting others. A Bragg grating is a periodic variation in the refractive index of the fiber core, regions of slightly higher and slightly lower refractive index alternating along the fiber. These gratings are typically created by exposing the fiber to ultraviolet light in a specific pattern. The UV light causes subtle changes in the glass structure, permanent modifications that alter the refractive index slightly. The periodicity of the grating determines which wavelength gets reflected. Light at the Bragg wavelength reflects strongly from the grating, while other wavelengths pass through largely unaffected. Fiber Bragg gratings serve many purposes. They can be used as mirrors in fiber lasers, as wavelength-selective filters in communication systems, as sensors that detect strain or temperature changes based on shifts in the reflected wavelength. They represent another example of how glass can be precisely engineered at the microscopic level to control light. For long-distance communication, one of the fundamental challenges is signal loss. Even the purest optical fiber absorbs some light. Over tens or hundreds of kilometers, signals weaken to the point where they can no longer be detected reliably. The solution is amplification. But how do you amplify a light signal traveling through a fiber? The elegant answer is rare earth-doped glass fibers that amplify light signals directly in the optical domain, without converting to electricity and back. These are called optical amplifiers, and the most common type uses erbium-doped fiber. Erbium is a rare earth element, and when incorporated into silica glass fiber, it has a remarkable property. When illuminated with light of one wavelength, typically from a pump laser, it can amplify light of another wavelength that happens to be the wavelength used for telecommunications. The physics involves quantum mechanics. The pump light excites erbium ions to a higher energy state. When signal light passes through, it stimulates these excited ions to drop back down, emitting additional light at the signal wavelength. The result is that weak signals can be boosted back up to full strength without any electronic conversion. This is crucial for long-distance fiber-optic systems, allowing signals to travel thousands of kilometers with periodic optical amplification. But amplifying signals is not enough. As data rates increase, another problem emerges: dispersion. Different wavelengths, and even different parts of pulses at the same wavelength, travel at slightly different speeds through fiber. Over long distances, this causes pulses to spread out, to blur into each other, making it impossible to distinguish individual bits of data. Dispersion-engineered fibers prevent data blurring through careful control of the fiber's optical properties. Standard single-mode fiber has inherent dispersion characteristics that limit data rates at certain wavelengths. But by adjusting the fiber design, changing the core size, altering the refractive index profile, modifying the waveguide structure, engineers can create fibers with different dispersion properties. Some fibers are designed to have zero dispersion at specific wavelengths. Others are designed to have dispersion that counteracts the dispersion accumulated in other parts of the system. This dispersion management is crucial for high-speed, long-distance transmission. It's another example of how glass composition and structure can be precisely tailored to meet specific performance requirements. Even with perfect amplification and dispersion management, a single fiber can only carry so much data on a single wavelength of light. To meet ever-growing demand for capacity, engineers developed wavelength division multiplexing, a technique that sends many colors at once through the same fiber. Instead of using just one wavelength, a WDM system might use dozens or even hundreds of different wavelengths, each carrying its own independent data stream. Think of it like different radio stations broadcasting at different frequencies. You can tune to different stations even though all the signals travel through the same space. Similarly, different wavelengths of light can travel through the same fiber, each carrying different data, without interfering with each other. At the receiving end, the different wavelengths are separated by optical filters or gratings, and each is detected independently. This transforms capacity dramatically. One fiber becomes many virtual data lanes, each lane carrying data at high speed. A fiber that might carry 10 gigabits per second on a single wavelength can carry 100 wavelengths, and thus transmit a terabit per second, a trillion bits per second. This multiplication of capacity through wavelength division has been crucial to meeting internet bandwidth demand over the past few decades. But engineers didn't stop there. Recently, space division multiplexing adds spatial channels by using multiple cores in a single fiber, or by using different spatial modes within a single core. Multi-core fibers contain several independent cores within one fiber cladding, essentially multiple fibers bundled together at the glass level. Each core can carry its own wavelength division multiplexed signal, multiplying capacity yet again. Mode division multiplexing uses the fact that light can propagate through fiber in different spatial patterns, called modes. By carefully controlling how light is launched into the fiber and extracted from it, engineers can use these different modes as independent channels. It's complex. The modes can couple to each other, causing crosstalk that must be managed. But it represents another dimension in which fiber capacity can be expanded. All of these technologies, photonic crystal fibers, Bragg gratings, rare earth-doped amplifiers, dispersion management, wavelength multiplexing, space multiplexing, come together in the systems that form the backbone of global communication. Perhaps nowhere is this more impressive than in the undersea fiber cables that span entire oceans, connecting continents with strands of glass lying on the seafloor. These cables are engineering marvels. They contain multiple fiber pairs, each capable of carrying terabits of data per second using wavelength division multiplexing. They include optical amplifiers, spaced every 50 to 100 kilometers along the cable length, powered by electrical conductors that run alongside the fibers. They are armored to protect against ship anchors and fishing gear in shallow waters, streamlined for deep ocean deployment. Laying these cables requires specialized ships, careful route planning to avoid geological hazards, and extraordinary precision. Once installed, an undersea cable might operate for 25 years or more, carrying a substantial fraction of intercontinental internet traffic. When you stream a video, make a video call, send an email across an ocean, there's a good chance your data is flowing through one of these undersea cables, traveling as pulses of light through glass fibers, lying in the cold darkness thousands of meters below the ocean surface. The scale of the global fiber network is difficult to comprehend. Millions of kilometers of fiber-optic cable span the world, running under oceans, buried beneath streets, strung on poles, threaded through buildings. And through all of this glass, most of the world's information flows. Glass carries most of the world's information: text, images, video, voice, financial transactions, scientific data, entertainment, news, social media, everything that constitutes our digital existence. Think about what this means. Glass, that ancient material that humans first encountered as volcanic obsidian, that early civilizations accidentally created in furnaces, that Romans learned to blow into vessels and windows. This same material, refined and perfected, now carries the data that defines modern life. The medium that once carried light across a few centimeters of window pane now carries information across oceans, around the world, instantaneously. The internet feels invisible, intangible, virtual. We speak of the cloud as if our data floats somewhere in an ethereal realm. But the reality is physical, material, tangible. Most internet traffic, at some point in its journey, travels through glass. The fiber in the ground, under the ocean, in the walls. This is the physical substrate of our information age. Glass is not just the window through which we see the digital world. It is the medium through which the digital world exists and flows. And the demand continues to grow. Video streaming, cloud computing, artificial intelligence, virtual reality. Each generation of applications demands more bandwidth, more capacity, more bits per second flowing through the network. Engineers continue to push fiber technology forward, finding new ways to squeeze more capacity from each strand of glass, developing new fiber designs, new multiplexing schemes, new amplification techniques. The photonic crystal fibers represent one frontier, exotic structures that control light in novel ways. Space division multiplexing represents another, using the physical dimensions of the fiber more efficiently. Researchers are exploring multi-band transmission, using wavelength ranges in fiber that weren't previously used for communication. They're developing better modulation formats, more sophisticated error correction, more efficient ways to encode information onto light. Each advance requires deeper understanding of how light propagates through glass, how nonlinear effects arise at high powers, how to manage impairments, how to design systems that work reliably over thousands of kilometers. It's a combination of physics, materials science, electrical engineering, and computer science, all focused on making glass carry more information, faster, farther, more reliably. As you rest now, think about the data flowing around you, through you, beneath you. In the walls of your building, under the streets outside, crossing the ocean floors. Photons are streaming through glass fibers, pulsing with information, carrying the digital traffic of billions of people and countless machines. The light is invisible, the fibers are buried or submerged, but the flow is constant, immense, essential. Glass has become the nervous system of global civilization. Just as nerves carry signals through your body, allowing communication between brain and limbs, between senses and consciousness, glass fibers carry signals through the world, connecting devices and data centers, connecting people across distances, connecting the distributed intelligence of the internet into a functioning whole. And it all depends on glass, on the purity of the silica, on the precision of the fiber structure, on the careful engineering of dopants and coatings and geometries. Glass, in its most refined form, has become not just a material, but an enabling technology, the physical foundation on which the information age is built. The ancient material has found its most sophisticated application. From cutting tools to windows to lenses to communication fibers, glass has accompanied human civilization, has evolved with it, has enabled each new stage of technological development. And now, as information becomes the currency of the modern world, glass has become the medium through which that information flows. Rest with the knowledge that beneath the abstraction of digital life lies something concrete. Glass. Strands of it, millions of kilometers of it, precisely made, carefully installed, constantly carrying the light that carries the data that constitutes so much of modern existence. The cloud has a physical form, and much of that form is glass, stretched thin, optimized for transparency, engineered to guide light across the world. The mystery of glass, that paradoxical material, neither quite solid nor quite liquid, has become the foundation of global communication. The ancient and the modern, the simple and the sophisticated, the familiar and the exotic, all combined in these hair-thin fibers that carry civilization's information, one photon at a time. We have traveled far in our exploration of glass, from volcanic obsidian to smartphone screens, from ancient beads to global communication networks. But our journey is not quite complete. Glass has woven itself so thoroughly into the fabric of modern life that its presence extends into places and applications that might surprise you, into technologies still emerging, into futures still being invented. Glass is everywhere, quietly enabling, silently supporting, constantly present, yet often invisible. Consider a seemingly simple advantage of glass fibers that has profound implications. Glass fibers are immune to electromagnetic interference. They carry light, not electrical current, and light propagating through glass is unaffected by magnetic fields, by radio waves, by the electromagnetic noise that pervades modern industrial environments. This immunity makes glass fibers invaluable in settings where electromagnetic interference would wreak havoc on copper wires. And so, they are used in factories and power systems, in environments filled with electrical machinery, with motors and transformers and high-voltage equipment that generate powerful electromagnetic fields. In a power plant or an electrical substation, monitoring and control signals must flow reliably despite the intense electromagnetic environment. Copper wires in such settings can pick up interference, can have signals corrupted, can even couple with power systems in dangerous ways. Glass fibers solve these problems elegantly. They carry signals with perfect immunity to electromagnetic disturbance. In industrial automation, in manufacturing facilities with heavy machinery and welding equipment and motor drives, glass fibers allow reliable communication. The control networks that coordinate complex manufacturing processes, that synchronize robots and sensors and actuators, increasingly rely on fiber-optic communication for its immunity to interference, for its reliability, for its ability to carry high-speed data in electromagnetically hostile environments. But glass fibers do more than simply carry information from one point to another. They can also sense, can measure, can monitor their environment along their entire length. Distributed fiber sensing measures strain and temperature continuously along a fiber, transforming the entire length of the fiber into a sensor. The technique uses subtle changes in how light scatters within the fiber, changes caused by temperature or mechanical strain, to determine conditions at every point along the fiber. This creates extraordinary possibilities. A single fiber, kilometers long, becomes thousands or millions of individual sensor points. The fiber can be embedded in structures, in bridges, in pipelines, in dams, and monitor the health of that structure, detecting strain, deformation, temperature anomalies that might indicate damage or failure. The fiber can be buried alongside roads or railways to detect traffic, to sense unauthorized digging, to monitor ground stability. Glass fibers are used in oil and gas wells, lowered thousands of meters into the earth to monitor temperature and pressure during drilling and production. Traditional well monitoring uses discrete sensors at specific depths, providing only sparse data. Fiber-optic distributed sensing provides continuous measurement along the entire wellbore, revealing temperature profiles that indicate where oil or gas is flowing, detecting problems like fluid leaks or blockages, optimizing production in ways that discrete sensors cannot match. The fibers must survive harsh environments, high temperatures, high pressures, corrosive fluids. But specially designed fibers can endure these conditions, providing data from deep within the earth, guiding decisions about how to extract resources efficiently and safely. Beyond sensing, glass offers advantages of weight and performance that make it valuable in demanding applications. Aerospace systems use glass to reduce weight compared to traditional materials. Glass fiber composites, glass fibers embedded in polymer matrices, provide high strength at low weight, crucial for aircraft and spacecraft, where every kilogram matters. Glass fibers reinforce structures, carry loads, enable lightweight designs that would be impossible with heavier materials. Optical fibers themselves weigh far less than the copper wires they replace. In an aircraft with hundreds of sensors and control systems, replacing copper data buses with fiber-optic networks can save substantial weight. Weight that translates directly into fuel savings or increased payload capacity. Modern commercial aircraft and military planes increasingly use fiber-optic communication systems throughout, taking advantage not just of electromagnetic immunity, but also of weight savings. In medicine, glass has enabled entirely new ways of seeing inside the human body. Medical endoscopes rely on fiber bundles, thousands of individual optical fibers bound together, each carrying a pixel of an image. The bundle is flexible, can be threaded through natural or surgical openings, can illuminate internal organs, and carry back images to the physician's eye or to a camera. Modern endoscopes are sophisticated instruments, combining fiber optics for imaging with working channels for instruments, with fiber-delivered light for illumination, enabling minimally invasive procedures that would have required open surgery in earlier eras. A physician can examine the interior of a patient's stomach, can inspect joints, can navigate through airways or blood vessels, all through glass fibers thin enough to thread through the body with minimal trauma. Glass also delivers therapeutic power. Fiber-delivered lasers enable precision surgery, carrying intense laser light from a source outside the body to exactly where it's needed inside. Laser surgery for vision correction, for removing tumors, for clearing blocked arteries, for countless other procedures. Much of this relies on optical fibers to deliver the laser energy precisely, controllably, to the treatment site. The fiber acts as a surgical tool, allowing the physician to work at a distance, to reach places that would be difficult or impossible to access directly, to apply energy with precision that reduces damage to surrounding tissue. The same glass that carries data across oceans carries laser light through blood vessels, enabling medical procedures that save and improve lives. As we look toward the future, glass continues to enable emerging technologies that seem almost like science fiction. Quantum communication uses single photons in glass fibers to transmit information in ways that are fundamentally secure. Quantum mechanics guarantees that any attempt to intercept or measure these photons will disturb them in detectable ways, making quantum communication theoretically unbreakable. Researchers and companies are building quantum communication networks, using optical fibers to distribute quantum encrypted keys between locations. These networks could eventually secure financial transactions, government communications, any data that requires absolute security. China has built a quantum communication network spanning thousands of kilometers. Europe, and the United States are developing similar systems. All of them rely on glass fibers to carry individual photons without disturbing their delicate quantum states. The same fibers that carry billions of photons per second in conventional communication can be used to carry single photons for quantum applications. It's a testament to the quality of modern optical fiber, so pure, so well characterized, that it can support both classical communication at terabit speeds and quantum communication at the single photon level. Glass is also becoming integrated into computing itself. Integrated photonic chips route light through glass waveguides etched onto silicon or other substrates, creating optical circuits analogous to electronic circuits. These photonic chips can process optical signals without converting to electronics, enabling faster data processing, lower power consumption, more efficient ways to move data within and between computers. Data centers, the buildings full of servers that power cloud computing, that host websites and services and applications, increasingly use photonic interconnects to move data between racks of equipment. The data travels as light through glass waveguides on circuit boards, through optical fibers between racks, only converting to electronics at the last moment when it needs to be processed by a chip. This optical data movement is more efficient, generates less heat, allows higher data rates than purely electronic interconnects. Future computers might integrate photonics more deeply, using light rather than electricity for computation itself in certain applications. Optical computing remains challenging. Light doesn't interact with light the way electrons interact with each other, making logical operations more difficult. But for certain tasks, especially those involving moving large amounts of data quickly, photonics offers compelling advantages. And so we arrive at the culmination of our journey. The same mysterious material still shapes our future. Glass, which began as nature's accident in volcanic flows, which humans learned to make in ancient furnaces, which enabled windows and lenses and global communication. This same glass, still not fully understood at the most fundamental level, continues to enable new technologies, new applications, new ways of sensing and communicating and healing and computing. The atoms in modern optical fiber are arranged in the same disordered, liquid-like pattern as the atoms in ancient Roman glass, as the atoms in obsidian that formed millions of years ago. Glass remains an amorphous solid, a material in that paradoxical state between liquid and solid, a material that still puzzles physicists seeking to understand the glass transition. Yet this mysterious material has become essential to modern civilization in ways that would astonish ancient glassmakers. The Mesopotamian artisan who first deliberately made glass, the Roman glassblower who shaped vessels, the medieval craftsperson who created stained glass windows. None could have imagined optical fibers carrying terabits of data per second, or distributed sensors monitoring pipelines, or quantum communication securing messages, or glass enabling surgery inside the human body. Glass has accompanied humanity on its journey from prehistory to the present and onward into the future. It has adapted, has been refined, has been reimagined countless times. From solid objects to hair-thin fibers, from colored art glass to ultra-pure transmission fiber, from crude ancient techniques to nanoscale engineering, glass has evolved while retaining its essential nature. As you settle into sleep, let your mind rest with this thought. The world around you, the technological civilization you inhabit, rests substantially on glass. Not just the windows you see through, though those remain important. Not just the screens you look at, though those are everywhere. But the invisible infrastructure, the fibers underground and underwater, the sensors in structures and wells, the medical devices, the aerospace components, the photonic chips beginning to appear in data centers. Glass is the quiet foundation, the enabling material, the substance that makes so much else possible. It carries our information, senses our infrastructure, enables our medicine, lightens our aircraft, secures our communications. It does all of this while remaining, at its core, that same strange material. Neither quite solid nor quite liquid, disordered yet stable, ancient yet cutting edge. The mystery persists. Researchers still work to fully understand the glass transition, to explain why some materials form glasses easily while others resist, to predict glass properties from first principles. The fundamental physics of glass remains an active area of research, an unsolved problem that attracts curious minds. Yet the practical mastery of glass continues to advance. Engineers develop new compositions, new structures, new applications. The photonic crystal fibers with their intricate air-hole patterns, the quantum communication systems with their single-photon precision, the integrated photonics chips with their glass waveguides. Each represents glass pushed to new frontiers, glass shaped and controlled in ways that expand what the material can do. This is the beautiful duality of glass. Profoundly useful yet not fully understood, ancient yet modern, simple yet complex, transparent yet mysterious. It is ordinary. You encounter it every day, barely notice it, take it for granted. Yet it is extraordinary, enabling technologies that connect the world, that extend human senses, that make possible the information age. Glass has been many things to humanity. Tool and treasure, container and window, lens and fiber, art and technology. It has changed how we see, both literally, through lenses and microscopes and telescopes, and metaphorically, by revealing the very small and the very distant. It has changed how we communicate, making distance nearly irrelevant, connecting billions of people into networks of information exchange. And glass will continue to shape the future. New applications are being invented, new uses discovered, new techniques developed. Perhaps glass will enable quantum computers, carrying and processing quantum information. Perhaps it will enable new forms of sensing, new ways of imaging, new medical treatments. Perhaps discoveries we cannot yet imagine. The story of glass is not finished. It continues in research laboratories, in manufacturing facilities, in the minds of scientists and engineers, who see in glass not just what it has been, but what it might become. The material that has served humanity for 5,000 years shows no sign of becoming obsolete, no indication that we have exhausted its possibilities. So rest now, surrounded by glass in forms you can see and forms you cannot. The window, perhaps, letting in light or keeping out cold. The screen, if you have one nearby, displaying information. The fibers underground or in walls, carrying data silently, constantly. The medical devices in hospitals, enabling diagnosis and treatment. The sensors in infrastructure, monitoring for safety. The global network of glass connecting continents, carrying civilizations' information. All of it glass. All of it that strange, paradoxical, not quite solid, not quite liquid material that nature made in volcanoes and humans learned to make in furnaces. All of it fundamentally the same as it has always been, atoms frozen in disorder, yet transformed through human ingenuity into structures and applications of extraordinary sophistication. The mystery of glass remains, but the utility of glass, the versatility of glass, the indispensability of glass, these are clear. From obsidian blades to quantum communication, from ancient beads to photonic chips, glass has been there, enabling, supporting, quietly shaping human history and human future. Sleep now, knowing that the material world is stranger and more wonderful than it appears. Glass, transparent and overlooked, is neither simple nor fully understood. It is a reminder that mysteries remain even in the most familiar materials, that wonder exists not just in exotic phenomena, but in everyday substances, that the ordinary can be extraordinary when examined closely. Glass carries light. Glass carries information. Glass carries humanity forward, one photon at a time, one fiber at a time, one application at a time, into a future that will surely be shaped, in part, by this ancient, mysterious, indispensable material. Rest well, and let the quiet presence of glass, in windows and screens, in fibers and sensors, in the foundations of modern life, remind you that the world is built on substances both practical and profound, both understood and mysterious, both ancient and endlessly new. The mystery of glass endures, and so does its gift to humanity.